Hi, my name is Dana Golden, and today we're going to talk about neural networks and data sources. Neural networks have changed the field of machine learning dramatically. When I got started in machine learning, it was kind of viewed as the same as classical statistics. It was, classical statistics with a little bit of a wink. You had tree models, you had random forest, but overall, you mainly knew what you were doing, and you mainly were not working with massive black boxes that could do things that were completely out of the realm of classical statistics. Neural networks are different. They are powerful tools for fitting complex functions using large data sets. They're widely used in tasks like games, computer vision, natural language processing, and chatbots. They have been adopted more slowly in economics because a key challenge is causality. Central concern in economics, but extremely hard to extract from the black box nature of neural networks. Progress is being made on explainable interpretable models. It's not going to get there. These fundamentally, kind of the point is that you don't know what it's exactly doing all the time. You know roughly what it's doing, but you don't know what data it looks at because it's supposed to be incredibly complicated. Most use cases involve labeling for unprocessed data and handling unstructured data and prediction tasks. Neural networks are also emerging in dynamic modeling in areas like macroeconomics and industrial organization in economics. At a basic level, neural networks are made of layers that apply linear transformations followed by nonlinear activation functions. Stacking multiple layers allows the model to learn complex patterns beyond what a single logistic or linear regression could capture. So here's gradient descent. As you know, if you start with initial weight, you have a learning rate, and you go to a new weight. Normally, the learning rate declines as you decrease because either the gradient goes down or you have a learning rate that automatically declines through a process like Newton's method. So go down, go down, go down. Maybe you overshoot it, and then you roll down the hill. The idea is you're getting to the bottom of the hill. Neural networks gradient descent helps neural networks by updating their weight by minimizing the prediction error step by step. Forward propagation moves data through the network from input to output. The simplest form is a linear transformation followed by nonlinear activation, like logistic regression. Other types of layers can be added, such as convolutional layers, recurrent layers, depending on the task. In a neural network, each layer transforms the data before passing it to the next. The layered structure allows the model to build up complex understanding step by step. Each node can learn to detect a specific feature from the input. As layers go deeper, they combine earlier features to recognize more abstract patterns. Successive layers in neural network can combine combinations of different features in earlier layers to recognize more interesting patterns in the data. Pixels go to edges, to shapes, to objects. Activation functions introduce nonlinearity between layers. They allow neural networks to model complex nonlinear relationships. Without activation functions, even deep neural networks would behave like a simple linear model. Common examples of activation functions include ReLU, rectified linear unit, sigmoid, and 10H. So here's some activation functions. You see sigmoid, it is the logistic activation function that we saw earlier. It starts off low and it goes high, anything with 10H. Rectified linear unit, it's useful because it helps with the gradient explosion and gradient gradient decay, and it's the max between 0 and x, so it increases linearly. The derivative is just 1 if it's greater than 0, and it's 0 if it's less than 0. And then, of course, you have other major activation functions, but these are the main ones. Sigmoid is primarily used for classification. ReLU is used in all sorts of neural networks because of its interesting properties. Automatic differentiation computes derivatives automatically by building a computation graph. It tracks each operation, applies a chain rule to compute gradients efficiently. Everything is chain rule. When in doubt, chain rule. So here's an automatic differentiation graph. We go from the loss, and then we go back to the operations, and then to the weights, and then we go to the operations, then weights, then the bias, and then the weights. Each node is represented by an operation. Arrows track how values and gradients flow through the network, and you just multiply earlier gradients by later gradients. Once we compute gradients using automatic differentiation, we need a way to apply them to the entire network. Backpropagation is the algorithm that efficiently computes how much each weight contributes to the overall loss. So backpropagation is very special because it uses the chain rule to find the gradients of the loss function with respect to each parameter. It moves backwards from the very end to the start, and it saves later gradient calculations to be used in earlier gradient calculations. Gradients used to update the weights and biases during training. The process moves backward to the network, which allows it to save some memory and computation. So gradients are passed backwards through the loss through each layer to adjust parameters. So it goes from the output layer to the input layer through each of the hidden layers. Logistic regression is a one-layer neural network. Logistic regression is actually a very simple neural network. It has one layer followed by a sigmoid activation function. So that can be seen as a single-layer perceptron. Many early neural networks were built by stacking such layers. These are called multi-layer perceptrons. The output depends on the last linear layer, the activation function applied to it, and the cost used for training. Number of outputs from the last layer determine the input size of the final activation. This is very important. Think about a neural network as multiplying together a bunch of matrices. And when you're multiplying a bunch of matrices, you need to know the shapes and how they relate. So think about that. Write down the shapes of all the matrix objects and make sure that they match. This is a big deal when you're multiplying matrices and when you're creating a neural network, because if the matrices don't match, it's going to fail. Not as big a deal as when I got started here, but still a pretty big deal. An activation function depends on the task. Sigmoid is for binary input. Softmax is multi-class classification. And then nonlinear is regression. So which loss function fits each case? Classification obviously uses a binary cross-entropy loss or a categorical cross-entropy loss where you're penalizing being wrong about the class. Regression uses mean squared error or mean absolute error, depending on your regression goal. And then you have other loss functions for other primary tasks. And that is that.